Welcome back. Let's get into another problem. And so this problem has to deal with the instantaneous center of zero velocity. And I will describe that a little bit more in a moment or two, but let's read the problem statement. So we have this rigid length that is constrained to move in the horizontal and vertical directions of blocks x and y. So as you can see, we're being rotated by some angular velocity omega, and due to the constraint, x and y are either going to move horizontally or vertically. We're given some geometrical data for the length of the link, and as well as the angular velocity, which is 3 radians per second. And we are being asked to determine the speeds of x and z, respectively, specifically whenever theta is 30 degrees. So I went ahead and I wrote out our given. So we have x and y, the distance from y to z, as well as omega and theta. We're asked to determine the speeds x and z. Okay, so as I said before, this is going to be an instantaneous center of zero velocity problem. And just to kind of recap on what that concept is if we have some point, say we'll call it x here, we'll be looking here at x, and what we want to do is we want to consider another point such that from its perspective, x is moving purely in a circular motion. And by doing that, we know that we could write an equation such that omega is going to be equal to the velocity of said point divided by the radial distance, or the perpendicular distance from that point and x. So we'll just call that xc maybe. Okay, and that's our general formula for having the circular rotation with an angular velocity in a radial bar and then your tangential velocity. And so if we then considered another point, we then would have our instantaneous center of zero velocity. So if we look back at our picture, we see that x is constrained to move in the horizontal direction. And likewise, so can y, but in the vertical direction. You can imagine if we're going to spin it counterclockwise, that x is going to be pushed to the right, and at least in this moment considered, and then y would be probably going down. Okay, so maybe if we draw our velocity vectors here, we just have something like this. Oh, it's a bad one for, oh no. Okay, here we go. Those are our velocity vectors for x and y. And so if we went ahead and did the instantaneous center of zero velocity idea, we want something perpendicular to the velocity of x so that we can use this equation. We want something perpendicular to velocity of y. Okay? And where they intersect is going to be our instantaneous center of zero velocity. So the idea of using this tool, this instantaneous center of zero velocity, is that we are uniquely choosing a reference point that momentarily has a velocity of zero. So at theta equals 30 degrees, at this specific orientation, it has zero velocity. So it's not a fixed point, it can change. And by using this tool for analysis, it allows us to analyze velocity in various plane motion various plane motion problems. And so there's our instantaneous center of zero velocity in this problem. And I'll just call it C. Okay? So there's our problem set up. And because we're going to need this Rxc value, we'll call it Yc, and we'll call this Xc, because we're going to need that later on. Okay? So now it's just a matter of finding the relevant geometrical values so that we can ultimately calculate everything that's going on. So first off, we want to determine Vx. So Vx is just going to be omega times xc. And xc we can determine from trigonometry. That is just going to be it's going to be xy, and then sine theta. Did everyone see how I got that? We're just using this box right here, and we're using our simple trigonometry. Okay, we know omega, that was 3 radians per second. We know xy, that's 0.75 meters. And we know theta, which is 30. So if we plug that all in, we'll get the speed of block x is 1.125 meters per second. Okay, great. Now we just got to do the same thing for Vz. So we'll just write Vz is going to be equal to omega times, what do we want to call this guy? We'll call it Zc, where that represents the distance from z to the instantaneous center of zero velocity. So I'll draw that in now. Hopefully that's not too bad of a drawing. And okay, so now our goal is to determine Zc. And just to demonstrate how we have our instantaneous center of zero velocity, remember we need Zc and Vc to be perpendicular. So the velocity of z is going to be something like that whenever we're rotating by omega. And so as you can probably see in this picture that I drew here, we have a triangle. If I draw this angle out here, or that line out here, we can put theta here. And so then that makes this angle, we'll call omega, where we can just write omega is going to be 180 minus theta. Sorry. Okay, and so I hope by whenever you see this triangle, you are immediately thinking law of cosines. So we can just write Zc squared is going to be equal to Zy squared plus Yc squared minus 2 Zy Yc, and then cosine gamma. We know gamma is going to be 150 degrees. And so there's our law of cosines. Our goal is to determine Zc. We know Zy, that's just Yz, which was 0.75 meters, which was given in the problem statement. We can determine Yc from trigonometry. And we know gamma. So we'll just simplify this down a bit more. So that's going to be equal to, okay, Zy. I'm just going to leave it in terms of its variables. Okay, Yc, let's look at this problem here. We have our triangle given by theta, so we can do simple trigonometry. That's going to be xy cosine theta, entire quantity squared, minus 2 Zy, xy cosine theta, cosine gamma. And we're just going to drop the square root, or drop the square and take a square root. And by doing that, you'll see that Zc is about 1.352 meters long. Okay? And now that we have that, we can just simply plug in here. Right? So that's going to give us Vz is just going to be 4.056 meters per second. And that's a wrap. That's our entire problem. So to summarize, we use the instantaneous center of zero velocity, and this worked because, or the idea of using that is that we are uniquely choosing a reference point that momentarily has zero velocity. And that can greatly simplify our plane motion velocity equations whenever we are dealing with some kind of rotating rigid body. And so I hope this was helpful. I hope this was a good problem that demonstrated the use of this instantaneous center of zero velocity tool, and I hope to see you around for the next video. Thank you.